We will now see what happens when the MOS capacitor is not ideal. It will be much easier to understand in terms of flat band voltage. We know the flat band voltage is 0 for ideal MOS capacitor. Let's assume the conditions one by one. First, we consider the case when the metal semiconductor work function is not equal to 0. In this case, we have a voltage corresponding to metal to semiconductor work function difference. To cancel the effect of this voltage, we have to apply the same voltage. This is because the potential drop across the metal and semiconductor pushes the charge carriers to move from metal to semiconductor or even vice versa. However, when an external voltage is also applied, then there is no movement of charge carriers and there is no bending in energy bands, so that our condition of flat band is achieved. Conclusion of our first case is, if the metal to semiconductor work function is not equal to 0, then we have to apply the same voltage at gate terminal for achieving flat band condition. Now come to the second case where the oxide is having trapped charges. During the manufacturing stage, some charge, mostly positive charge, gets deposited near the metal oxide interface. Being a capacitor, the other plate of the MOS capacitor, which is semiconductor oxide interface, respond to this deposited charge, and same magnitude of charge with opposite polarity gets deposited here also. These charges again create bands which affects the flat band voltage. In this case, flat band voltage is equal to charge per unit area on the metal oxide interface divided by capacitance per unit area of the oxide. But we usually consider charge on the semiconductor side because it is much easier to calculate the area of the rectangle rather than to calculate the area of an arrow, which we usually use to represent charge distribution on the metal, as we have considered it to be ideal, and ideally the charge should be present at the surface only. So the flattened voltage will be equal to negative of charge deposited per unit area on the semiconductor side divided by capacitance per unit area. We have considered both conditions of non-ideality separately. Now we will consider both cases simultaneously. In this case, we have to simply superimpose the flat band voltage of either case. This formula is valid irrespective of whether the semiconductor substrate is p-type or n-type substrate. One may think, what changes these non-ideal conditions make in the analysis of MOS capacitor? Well, the answer is not much. You will understand the best with the help of a graph. This is a graph of ideal p-type MOS capacitor. When we consider non-ideal MOS capacitor, then the whole graph shifts depending upon flat band voltage. I have assumed the new flattened voltage is positive for the shown graph. All the extreme values of range of different region changes, we have to simply add flat band voltage value in all of them. But the width of the range remains the same. Now consider another important parameter, which is threshold voltage. Threshold voltage will be equal to flat band voltage plus the threshold voltage which we got for ideal MOS capacitor. You should actually learn this form of threshold voltage as it considers both ideal and non-ideal MOS capacitor. For ideal case, you have to simply put flattened voltage to be equal to 0. Similarly, we can write the threshold voltage for non-ideal n-type substrate MOS capacitor. Depending upon these non-ideal conditions, the MOS capacitor is further divided into depletion and enhancement type MOS capacitor. Depletion MOS capacitor is the capacitor in which we need not to apply any voltage for getting the inversion channel. However, enhancement type MOS capacitor is the capacitor in which we have to apply certain voltage at the gate terminal so that an inversion layer channel is created. Now, the question is how depletion devices can be created. To understand this, again consider the graph of ideal p-type MOS capacitor. Now suppose that due to the non-ideality factor, the flat band voltage is sufficiently negative such that the threshold voltage becomes smaller than 0, so that there is no need of applying any voltage at the gate terminal to create inversion layer channel. If this condition is satisfied, then this device will be considered as depletion MOS capacitor. Otherwise, it will be considered enhancement type MOS capacitor. In case of N-type substrate MOS capacitor, we need the flat band voltage to be sufficiently positive so that the threshold voltage becomes greater than 0. In this case, large positive flat band voltage is required for having a depletion MOS capacitor. From the 4 diagrams we just considered, you can say that an ideal MOS capacitor can never be a depletion MOS capacitor. After all the lectures studied so far, everyone should be able to understand accumulation region, depletion region, inversion region, strong inversion region, threshold voltage, and flat band voltage are strictly defined in terms of surface potential, which is indirectly dependent upon Fermi potential. The conditions remain same for ideal and non-ideal case. However, the corresponding gate voltage will differ for non-ideal and ideal capacitor. The conditions for the range of different regions also differ depending upon the type of substrate used in MOS capacitor.